Okay, awesome. So then the things get a bit complicated because I'm not just going to have one non-FLO CZ gate in my circuit. I'm going to have a whole bunch of them. But the overall effect is going to be that if I try and compute some vulnerable probability of a circuit I gave of the form before, what you're going to get is you're going to get, let's see, something like this. I'm just going to say we're looking for the zero outcome on all of the qubits. Obviously, this can be any computational basis string. It doesn't really make a difference here. So we have n of these guys to start with. We have all these projectors onto M5s, M5 here. I'm just going to write a tensor product here and say there's k of them. Yeah. And then we're going to have an FLO unitary here. And then we're going to have our initial or zero state. Yeah. Okay. So this is just what you get from the picture before. Then you 0 tensor n. This ends up, okay, so each M was a sum of two fermionic Gaussian states. So the tensor product with k of them, or becomes a sum over 2 to the k guys when you multiply out all the brackets. So I'm just going to say this is a string of y in 0, 1 to the k, y tilde. This also depends on what your phi's were. U 0 squared. So this y tilde here, like, is going to be something like 0 tilde is a of phi. 1 tilde is going to be b of phi, and then with longer bit strings you get the tensor product. This is what this tilde notation here means. And the reason this sum is now quite cool is that each of the terms in this sum is now a completely fermionic Gaussian, like an FLO computation. So the 0 is an FLO state, the U is an FLO unitary, and the Y tildes are FLO guys because A and B were before. So each of the terms in this sum is an FLO thing that you can efficiently compute using, for example, well, okay, maybe you could use something like Barber-Turhel and algorithm or something like this, or something to do with one of Sergei Brav's algorithms. And all I really want to know is I want to know the well, okay, actually I'm not going to write this thing. All you can do is you stick the 0 in, you stick this 0 inside this sum, right? It's not very difficult to turn this thing into one like sum of complex numbers. So you get the sum of 2 to the k complex numbers. Each of these complex numbers you can compute using like standard FLO techniques, hopefully. Yeah. Doing this sum over 2 to the k terms turns out to be a bit stupid, and you can do something slightly better than this. If you use Hofting's inequality. Oh, he has an E in his name, right? Hofting's inequality. See? You can bound how many terms in the sum you have to do. You have to compute in order to get a kind of epsilon error in your approximation. I don't want to go through this in great detail because I don't want to spend a huge amount of time on it. But essentially everything in the FLO case works exactly the same as it does in the Clifford stabilizer case. And this was already worked out by Hakko Pashayan, Kamil Kozhekva, and me in a paper that came out last year. So essentially what you do is you come up with a bound on the number of terms in the sum you need to get an epsilon approximation of P, which goes in terms of a quantity known as the extent. So number of terms needed for epsilon approximation.
Sorry, Oliver, but instead of summing it up, you're just sampling the entries of the sum?
Yes, you sample some entries of the sum, and the extent tells you how many terms of the sum you need to sample in order to get an epsilon approximation of P.
Ah, okay. So that
Yeah, this
okay.
is the question.
Okay, yeah. That will parameterize the Hafting inequality. Yeah. Okay.
Yeah, exactly. Flex approach to P.
Okay.
So let's say you need S terms. Hafting's inequality tells you, how big S has to be. And this is exactly given in terms of a quantity known as the extent. So this is given by a quantity called the extent of the state M phi tensor K that we had before. And an easy upper bound on this thing is the product from J is 1 to K M phi. Oops. Let's say the kth one. The extent of each of them. Okay. So this is an upper bound. So in particular, what you can do is you can just compute the extent of each of the individual terms in your big tensor product and multiply them together to get a bound on the extent, the total extent.
But in this case, it will be the FLO extent, right?
Yeah. FLO.
Sure. Yeah.
I should also define this quantity. So if I have some set of states, let's say extent. If I have some set of states S, which I assume at least span the state space. The extent of some state is the inf of this quantity A, 1 norm squared, such that sum over S in S, A, S is phi. Okay. It's the minimum 1 norm squared such that you can come up with some decomposition of phi in terms of your free states. Okay, so here S is the FLO states. This is usually defined for stabilizer states, so where S is the stabilizer states, but you can do it for FLO states, it's completely fine. Okay. In the stabilizer state case, some interesting facts about the extent are known. It's not multiplicative. So this, in the stabilizer case, this inequality is an inequality, not an equality. There are explicit counterexamples. It is multiplicative for tensor products of states of up to 3 qubits. So for example, if I have a 2-qubit state, tensor product 3-qubit state, tensor product another 3-qubit state, tensor product 1-qubit state, then it's always multiplicative, right? But beyond that, for 4 qubits and higher, it is not multiplicative. In the FLO case, essentially nothing is known. I would say I know some facts about the extent. It's always submultiplicative, so this inequality is still true. I am trying to prove some facts about the multiplicity of the extent in the FLO case, but essentially I know nothing, and it turns out to be quite hard to prove anything concrete. But I'm working on this.
Is the super selection rule somehow disturbing, or?
You mean the parity? They have to be even?
Yeah.
Yeah, that's a good point. So the extent in the FLO case only really makes sense for fermionic states, so states of fixed parity.
And then given that constraint, it's harder to carry over those results for the 3-qubit extent, yeah? Or
I don't know. Yeah, I don't know how to at all.
But you're saying that, for example, that would be one thing that you would be trying, and that's already quite hard, yeah?
What do you mean?
So I think you mentioned it that the extent is multiplicative if we tensor up to 3-qubit states.
Yep.
Right.
The stabilizer extent is multiplicative, yes.
Yeah. And the FLO extent, we don't even know something similar, right? Because I was wondering maybe the proof technique would be still similar, but apparently something is different.
Okay, yeah. So the FLO guys have an interesting structure. So the extent we say only makes sense for even states, let's say, or fixed parity states.
Yeah.
Then any fixed parity state of less than 3 qubits is actually free. It's a fermionic Gaussian state. So
yeah, there are things like that, but there is a paper on, I think it was called I don't remember the name. There was some new term about something about some new aspect of correlations. Norbert Schuch was the first author.
Okay.
And they were showing that the rates are preserved if you have super selection rules. So I think that paper would imply that the kind of rate of the extent would be carried over from the qubit case to FLO. So,
what do you mean by the rate?
So for example, if you think about entanglement cost or something like this, the super selection rule of fermions might prohibit you to distill something. But they showed that if you go towards the asymptotic rate, this kind of decomposition from the symmetry doesn't disturb.
Okay.
So you can reach the same rate despite the constraint. In single shot cases, it's harder. It's just where it goes from. So maybe if you would be thinking about the many copy cases or something, it would be similar.
Yeah.
But if you're saying that it's trivial, because you also said that any free mode state is already Gaussian, or how was it?
Any free mode even parity, so fixed parity state is already Gaussian, yeah. Or 1, 2, or 3 modes, yeah. If you 1, 2, or 3 modes and even, then you're Gaussian as well.
No, on 2 modes I can have a non-Gaussian state, or? No. Okay.
And 2 modes, every even state is Gaussian. I think this is in this paper I linked, maybe even.
Yeah, no, I'm mixing up some numbers now.
Okay.
Okay. Let's just continue. I don't want to disturb too much because you said that you will need to finish the talk at some point, right?
I have a meeting at 11, so in like half an hour.
Okay. Yep.
Okay,
cool.
Sure.
Thanks so far.
We do know some facts about the extent. So one thing that I can say, essentially by like standard convex duality type arguments, you can prove that the extent of S of phi is, let's see, lower bounded by this quantity. It's the max over all states omega, the inner product of omega with phi over the fidelity of omega, where Fs omega is the max over I'm running out of letters now. S in S omega squared. Okay, so essentially proving something about the fidelity tells you some things about the extent. And an interesting fact that is true is that if you're okay, just in the case of FLO now, so if phi is given by a Clifford applied to an FLO state, let's say, I don't know, I ran a notation psi, where psi is fermionic Gaussian. Then actually the extent FLO of phi is exactly equal to 1 over the fidelity of phi. This is a kind of cool result. Yeah, this lower bound becomes tight if phi is a magic state for FLO that you get by starting with initial FLO state and applying a Clifford. This is just a something you can prove. This is essentially the extent of my knowledge about the FLO extent, is this fact. Okay, so I will talk in the very last, like, I don't know, 15 minutes, 10 minutes, about something which I didn't say before, which is if you look at this equation here where I'm trying to compute P, what you have to do is you have to add up, you have to compute a whole bunch of numbers that look like alpha y is, let's say, phi u 0, where this thing here is an FLO state and this u is an FLO unitary, right? This is essentially what the problem reduces to, and you have to compute not this explicitly and not phi u 0 like this, okay? And it turns out that this is not trivial, how to do the first one or the second one. As far as I know, no one really had a good way of doing this before. There's this result by Sergey Bravi and David Gossett, where they have this paper called something like Complexity of Quantum Impurity Models or Impurity Problems, something like this, which almost solves this problem. It solves it in a kind of special case, but it's not very like satisfying for our purposes. And essentially, I want to do this wherever U is a completely arbitrary FLO unitary, and these are completely arbitrary FLO states. I should say, sorry. This is still run. Right, we want like amplitudes, not probabilities, essentially is what we want. Okay, and it's not entirely clear how to do this. So if you go back to this paper that I cited earlier by Barbara Tuhal and DiVincenzo, where they tell you how to compute probabilities. Yeah, essentially what you always do is you end up conjugating by around the fermionic operators and C's by your unitaries, and phase information is lost, right? Because you do operations like Cj goes to U, Cj, U dagger, and if there's a phase on U, you lose it. And we have to kind of, in order to do this amplitude thing, in order to add up these complex numbers, we have to do something phase sensitive. So this problem was already a problem in the stabilizer like Clifford case, and this was solved in this paper, again, by Sergey Bravi, David Gossett, Dan Brown, Earl Campbell, some other people, which is called Simulating Quantum Circuits by Low-Rank Stabilizer Decompositions, where they invent the CH form for stabilizer states. Where they sort of deprojectivize this nice way, this stabilizer notation, and come up with a kind of phase sensitive way of doing a stabilizer computation in a sort of sensible, fast way, efficient way. And what they essentially, the punchline is that if phi is a stabilizer state, then it's equal to some complex number omega, UC, UH, S, where S is a computational basis state. UH has this form, product over J, Hadamard J to the Yj for some binary string Yj, and UC is a Clifford that maps 0 to 0. Okay, it's a Clifford and additionally maps 0 to 0, and omega is a complex number. Okay, this is the CH form for stabilizer states. And this essentially lets you phase sensitive stabilizer computation in an efficient way. And essentially what you do here, well, what happens here is all of the complexity, or most of the complexity of the stabilizer state is kind of represented in this UC guy here. And because UC maps 0 to 0, you can always keep track of the complex number 0, UC 0 is a norm 1 complex number. So you can kind of always keep track of the phase information in this complex number. Whereas if UC did not map 0 to 0, then at some point 0, I should say this is yeah, okay. You know the phase information essentially of this thing. and this, yeah, this lets you do kind of phase-sensitive stabilizer computation. So, okay, it turns out that you can do something very similar in the FLO case. Okay, so how do you do this? Very simply, you first think about what it means for an FLO unitary to map 0 to something proportional to 0, alpha 0. Well, you can write down this expression. Define this matrix HJI is 0, Ci, Cj 0. This looks like it comes out of nowhere. It kind of does come out of nowhere, but it turns out to be the right thing to do. And then look at what happens when I stick zeros in this expression. So, sorry, when I stick unitaries which preserve 0 in this expression. In particular, Ci, Cj 0 is equal to 0 U dagger Ci, Cj U 0. Right, because we're assuming that my U maps 0 to something proportional to 0, and then the U dagger term, the alpha from the U dagger term and the alpha from the U term cancel out because they're normal and complex numbers. Okay, but U is an FLO unitary. So in particular, okay, this is 0 U dagger Ci U dagger Cj U 0. I just stuck an extra U dagger in here. And then we know, because it's FLO, that U dagger Ci U is sum over J Rij Cj for some real orthogonal matrix R that we had before. So this is now equal to 0. I'm going to go quite fast here, sorry. Sum over Mn Rim Rjn Cn 0. Where I just applied this to each of, yeah, I just applied this kind of twice. And this is sum over Mn Rim Rjn H Ji, I think. If you pull the sum out of the product. Okay, so in particular, what you get is that U 0 is alpha 0 implies that this R matrix preserves H. Right, I can write this as R H transpose Ji. So this equals,
It should
yep.
be HMN or something and not HJI.
No, because I sum over M and N. I sum over M and N in this expression here, right?
Right.
Yeah, so there's no M stands left.
Okay.
Sorry, yeah, sorry, here you mean. Yeah, sorry, this should be MN, you're entirely right. Sorry, here,
Okay.
Yeah, this should be MN, you're completely right. Yeah, so yeah, but here it's JI. So this in particular implies that R H transpose is H. So R preserves this matrix H I defined. Okay. So now you can look at what this H is, and it turns out it has an interesting structure. If you can kind of just compute this, you get that H, if you maybe I've gone to another page. H is something like identity plus omega I, where, okay, this is the n by n identity, or 2n by 2n identity, sorry. And omega is this. It's a direct sum over J of blocks 1. Like this. So it looks something like 0, 1, minus 1, 0, 0, 1, minus 1, 0, 0, 1, minus 1, 0, n of these blocks, right? This has a useful name. This is one representation of a symplectic form. Omega is a symplectic form. Okay, we can go a step further actually. We can compute this operator, ij. I realize I'm going incredibly fast here, but so stop me if anything doesn't make sense. Ci, cj, and look at what this thing is. Why do we want to look at what this thing is? Well, we know that R preserves H. So if I apply U to this thing, U dagger, then essentially by the same reason I get before, I get sum over I, J, R, H, R transpose, I, J, C, I, C, J, which equals sum over I, J, H, I, J, C, I, C, J. So U preserves this thing here. And once again, you can compute this thing and discover that this thing is the number operator, which counts how many fermions are in my system. So, okay, we have the following chain of implications. U0 is alpha 0, implies that R omega R transpose is omega. This implies U n U dagger is n, which implies that that U actually preserves the number of fermions in the system, always. So we started with U maps 0 to 0, so it maps the state with no fermions to state with no fermions. Then we have that U preserves all of the number subspaces, essentially. So this actually also implies U0 is alpha 0 again. So these are actually, we sort of wrap around, and these are all actually equivalences, not just implications. So if you have a fermionic linear optical unitary which maps 0 to 0, then actually it keeps all the numbers, it preserves all the number subspaces. It preserves the number of unitary, it preserves the number of fermions.
Yeah, so that seems natural. It's only I don't see how you got the n operator, because we have this, let's say, Hamiltonian.
Mm-hmm.
So in the upper line there, you have equals to n.
Mm-hmm.
But why does it equal n? I missed that. Sorry. I mean, I agree. I agree with the statement, but just don't see that.
Okay, so essentially what you have to do is you have to look at this operator here and kind of explicitly compute it and just show that it equals n. Yeah. So like I don't really know how to prove this in a clean way. All I know how to do is to compute things like so essentially what you do to prove this is do Hij, Ci, Cj, some like bit string y, and show that this equals the Hamming weight of y times y, right? Mm-hmm. And then this is it. But I don't know a nice way to prove this other than just like explicitly do it in terms of matrices.
Yeah, so I guess so yeah, Baron.
Yeah, I guess it might help to like give like what we expect the definition of n to be, like outside of, apart from it turning out to coincide with that expression with the h, like what would be our reasonable expectation for an operator n, and maybe then we can see that.
And can you say again, Hij has some structure, or it's more or less anything that happens to be preserved? Because
sorry. So Hij is explicitly this operator, or is explicitly this number 0, Ci, Cj, 0.
So it's the vacuum covariance matrix, exactly. So it's this omega thingy.
Mm-hmm.
Okay, when it's omega, then I agree. Mm-hmm. When it's omega, then
it's identity plus omega, but it doesn't really matter.
Yeah. So when it's omega, you could also try to make maybe a dagger a in your notation operators.
Mm-hmm.
And then it's a simple block, and that becomes this number operator.
Yeah.
So
But
you
yeah,
could,
this step of the
Mhm.
proof I agree is ugly and it's not very nice, but yeah, it's true.
okay. Yeah, thanks.
Okay, for this thing. But so this thing I circled here is like the reasonable expectation of what you want from the number operator, right? If you apply it to a basis state, it should just count how many fermions are in it. Yeah. And then by linearity, it does the right thing on any fixed number of any like fixed number states. But this is what you wanted it to do.
Yeah,
And,
cool.
Yeah,
and it
that's
turns out that
useful,
it turns out that this operator here that you defined does this. So okay, cool. All right. So what we have now is the zero preserving FLO unitaries are what are also called passive FLO unitaries. They preserve the number of fermions you have. Okay, and then their associated R operators are not only just orthogonal matrices as they were before, but they're also symplectic. They preserve the symplectic form. Okay, now we go a little bit fast into something that gets called the KAK slash what's it called? Cartan decomposition. Okay. And this essentially says if I have any R, so any orthogonal matrix, I can write it in the following form. So R is orthogonal. It can be written in the form K1A K2, where okay, where K1 and K2 are orthogonal. Well, so all these matrices are orthogonal. K1 and K2 are also symplectic. So K1, K2 have a property like this. And A also has a nice form, which is a bit hard to write down, but A is block diagonal basically. So A is something like EXP alpha, where alpha is a direct sum of blocks 0, lambda j minus lambda j 0. Is this correct? Okay, so something like this is true. Okay, this took way longer than I expected. I was very slow, I think, explaining things. But okay. So we have this KAK Cartan decomposition of orthogonal matrices. We can essentially lift this to a decomposition of FLR unitaries. And what you get is maybe it's even easier if I do the stupid thing again and share screen here. And I can just share my notes again. Five. Yep. Okay. So this is a decomposition in terms of FLO unitaries. Sorry, in terms of orthogonal matrices, but essentially what you get is that K1 and K2 are symplectic, they preserve 0, and this thing in the middle is kind of maximally non-zero preserving, or maximally non-number preserving. So what this actually does is rotate you in subspaces of creating, essentially it creates fermions. Or it creates superpositions of having and not having fermions, let's say. This is
superpositions of two fermions, right? Those BCS.
Yeah, exactly. So they look like this WCS form. So it's easier to write this as here we go. Here, yeah. So this operator in the middle, is exactly this WCS form. It's a product over adjacent pairs, exactly.
Yeah.
Yeah.
So
Okay.
some call it block Messier transformation. This
Yeah, this block Messier transformation, exactly.
Mm-hmm.
It's block Messier form. And then, okay, from this, you can get a decomposition of arbitrary FLO states. What I do is I just apply U to initial vacuum state, because any FLO state can be obtained by applying an FLO unitary to initial vacuum state. This K2 is passive, so it maps 0 to 0. So it maps the vacuum state to the vacuum state. And an arbitrary FLO state is some K times this operator applied to the initial zero vacuum state. Which ends up looking like this. And I think 81 is the nicest way to get this. This is a very direct analog of the CH form known for like the stabilizer case. So any FLO state or any fermionic Gaussian state has this form. You have an additional vacuum state. You have this product out here, which creates superpositions of having and not having fermions in adjacent sites. So this is a pair of creation operators here. So you can, yeah, you can kind of see what this operator does. Like if I just take this product here to be a product, so only over 1J. So there's no product here, it's just a single term. Then what I get is like cos lambda j 0 plus sine lambda j 1, right? So yeah. And then yeah, once you've come up with once you've produced this big superposition over number states, you apply a passive unitary after that. And this is kind of the nicest thing we could have hoped for. It exactly mimics what happens in the Clifford stabilizer case. This like maps 0 to 0. This is a complex number. And in the stabilizer case, this was just a product of Hadamard's. Here it's a bit more complicated, but it does kind of the same job. It makes a sort of product of having and not having fermions. Okay. The very last ingredient we need essentially, so I don't have time to go through this at all, but the very last ingredient we need is to be able to apply FLO unitaries to states like this, and also do measurements on states in this form. So, okay, if you apply an FLO unitary to a state in this form, which is passive, then the application rule is very simple. You just combine the two cases, you multiply the two cases together. That's fine. If I apply an active FLO unitary to a state in this form, so a non-zero preserving guy or a non-number preserving guy, things get more complicated. But essentially, what you have to do is some like deprojectivization trick. You have to work out how to keep track of phases in a sensible way. And okay, I don't have time to go through this in detail, so I will just show it to you.
But that's all right, because we will have Lucas talking about the general group theoretic way.
Yeah.
So
but I thought it might be nice to have a specific way before you have a general
yeah,
way.
sure. But
yeah, but essentially all you have to do is compute terms like this. Yeah, which okay, you can do. I'll just leave it at that and say yes, you can do this.
That's the technical label,
apologize.
no? Because like the structure is you explained, and then you need to prove this 97 how to do it.
Yeah, exactly. Well, actually, yeah, you have to prove 97, and you also have to prove blah 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 blah, some complicated stuff. Where did this go? Yeah, you also have to prove 192, where you have two C's. Okay, it turns out to be convenient to be able to compute things like this. Essentially, the reason you need this is can I explain why you need this? Okay, no, I can't explain why you need this quickly, but it turns out you need to be able to prove compute this. And
the proof has an explicit form because you say there is an algorithm, but
yeah. The proof is an explicit form of the algorithm.
Okay.
I don't think I have it written here explicitly, but essentially what you have to do is you have to compute something like a Pfaffian of a matrix that looks like this.
Yeah,
the algorithm
that looks
just
familiar. That
yeah,
looks familiar.
you just yeah. yeah, you just mess around with these operators here until you end up with something which you can prove is the Pfaffian of something.
Yeah. All right. All right.
It's essentially given here, but yeah, it's also interesting.
Okay.
Okay. I think so I should say I think for me like the most interesting, well I have 1 minute left, so I don't want to take all of your time, so but what I really want to get a handle on is this FLO extent quantity and understand how it works. Like, if you guys have any ideas of how to work with these quantities, I'd be very interested. Because I've been trying to prove some results about it, and I'm essentially stuck. I don't know how to prove results about this FLO extent. It's quite complicated.
All right, great. So, unless somebody has a question while we have the recording, we would maybe stop the recording and. Or...
Yeah, sure. Thank you.
Okay, thanks so much, Oliver. Well, thank you. Okay. So.